Hello and welcome. In this lesson, we're going to talk about the probability distributions and the probability distribution function. We shall look at the probability distributions of a continuous random variable. So remember that there are two types of variables, or two types of random variables in probability distribution. We have the continuous and discrete. A discrete random variable will take numerical values, distinct numerical values such as 1, 2, 3, 4, and so on. These are mostly associated with countable variables, countable quantities, quantities that you can obtain their value by counting. The number of items in a bag, for example, the number of balls in a bag, they can be 2, they can be 5, but they cannot be a number like 2.5. But there are also the continuous random variables, and these are associated with quantities that takes continuous values in a given interval. A quantity, for example, if the value of a quantity is obtained by taking the measurement, for example, you want to get the height of a person, then this one can assume any value within a given interval. So such random variables, we shall call them continuous random variables. And in this section, we shall be looking at probability distribution associated with continuous random variables. So a continuous probability distribution is basically a probability distribution that is associated with continuous random variables. And as we have said, a continuous random variable can assume any value in a given interval. These variables are usually obtained by taking measurements, and sometimes we call them the measurable variables. So these variables, as I was saying, their values can be obtained by taking measurements. So sometimes we call them the measurable variables. We call them the measurable variables. So for a continuous random variable, if we make the class intervals smaller and smaller, and then plot the histograms, they will tend to form a smooth curve. So we think of a case where we have a set of data, and because we are talking about a continuous random variable which can take any value in a given interval. So when we take a value like between 1 and 2, there are infinitely many values that the variable can assume, because these are continuous values. So it any number between 1 and 2, and they are infinitely many. So when we have the frequency distribution, like we are given the class and the frequency, so that we can determine the class mark. Class mark is the midpoint of the class interval, such as between 1 and 2, we have the class size, or rather the class mark will be a value x, which is given as 1 plus 2 divided by 2. In this case, this is 3 over 2, which is 1.5. These are the values that we have here, the midpoint of the class interval. Then we can add the frequencies and get the sum of frequencies here, which in this case is 200. If you divide the frequency of a given class with the total frequency of the distribution, like 15 divided by 200, you get a value that we call the relative frequency of that class. Now, when you divide each of these with 200 and then add the results here, the sum of the relative frequencies, you should get a value of 1. You should get a value of 1. Then, now when we have the frequency distribution like this one, we can plot the class mark on the horizontal axis and the frequency on the vertical axis. What we get the bar grams, the bar diagram, we call it the histogram. Now we can take the midpoint of each of the midpoint of the tops of the bars here and join them with a smooth curve. If we consider the midpoints and join them with a smooth curve, we draw a curve passing through the midpoint of the tops of the bars. We get a curve that we call the frequency curve. So this information can be represented by a frequency curve. Now, the area under the frequency curve here, this area here, this area will be equals to the sum of frequencies, which in this case, in our case, it was 200. But if we divide the frequency of each class by the total frequency as we obtain, as we had said, we obtain a ratio that we call the relative frequency, and the sum of the relative frequencies is 1. Normally, this relative frequencies gives the probability of the random variable lying in a particular class. If we plot the relative frequency on the vertical axis and the class mark on the horizontal axis, we get a plot that we call the relative frequency curve. Now, the relative frequency curve will have the same shape as the frequency curve that we have here. But now, the area under the curve will be equals to the sum of the relative frequencies, which is 1. The total area under the curve here will be equals to the sum of the relative frequencies, which is 1 in this case. Sometimes we call this the probability curve, and the area under this curve is the total or the sum of the probabilities in the distribution. So as we have said, the curve has the same shape as the frequency curve, but the area under the curve equals the sum of the relative frequencies, which in this case represents the sum of probabilities in the distribution. If we can find the equation of this curve, then we shall call it the probability density function and denote it by f of x. Now, because the area under the curve represents the sum of probabilities, then which is 1, then we can write mathematically that the integral, remember, whenever we write the integral from some point A to B, f of x dx, this one represents the area under the curve. This represents when we have the point A there and B, the integral represents the area under the curve here between the ordinates x is equals to A and x is equals to B. So when we write this integral to represent this area. So for a probability distribution curve like the one we have here, we have said that the area under the curve, the entire area under the curve is equals to 1, so that we can talk of the integral from negative infinity to positive infinity of f of x dx must be equals to 1 whenever f of x is a probability density function. So this is the requirement that must be satisfied by any probability density function. So if we want to find the probability that the random variable lies within a given interval between x1 and x2, so in this case, whenever we have the curve and we want to find the probability that the random variable lies between some points x1 and x2, then we find the area under the curve bounded by the ordinates x1 and x2. So we write the probability that the random variable x lies between x1 and x2 is equals to the integral from x1 to x2 of f of x dx. So we simply integrate this function. Now we look at the mean and the variance of a continuous random variable. Now, in probability theory, a continuous random variable, as we have said, is a random variable that can assume any value within a certain interval, as opposed to the discrete random variable, which can take on a finite or countable number of values. Some examples of random variables may include the height, the weight of a person, the amount of rainfall in a certain area, or even the temperature of a room. These quantities can take any value within a given interval. So when dealing with the continuous random variables, we are interested in calculating their statistical properties, such as the mean and variance. The mean is also known as the expected value and is a measure of central tendency of a continuous random variable. It represents the average value of the variable of a given range. So the variance, on the other hand, measures the spread or the dispersion of the random variable around the mean. So to calculate the mean of a continuous random variable, we integrate the product of the random variable and its probability density function of a range of the variable. So similarly, to find the variance, we integrate the square of the difference between the variable and its mean multiplied by the probability density function of the range of the variable. So understanding the mean and variance of the random variable is important in many fields, which includes engineering. By analyzing the statistical properties of continuous random variables, one can make predictions about the behavior of a complex system and make informed decisions based on empirical data. So we consider a random variable x, whose probability density function is f of x, is known. So the mean, which we shall denote by x bar, and is also known as the expected value, and we write it as ex, the expected value of the random variable x, is defined as the integral from negative infinity to infinity of x times f of x. F of x is the probability density function. The variance, on the other hand, is the expected value of x minus the square of x minus x bar. So we can write the expected value of x minus x bar squared, where x bar is the mean. So this one is defined as the integral from minus infinity to infinity x minus x bar times f of x dx, which we can simplify and write it in this form. It is important to note that when we write x minus x bar squared, we can expand this and write x squared minus 2x x bar plus x bar squared. So when we write the integral from negative infinity to infinity x minus x bar squared multiplied by f of x dx, then we can substitute and write the integral from minus infinity to infinity x squared minus 2x x bar plus x bar squared, all this multiplied by f of x, and we integrate with respect to x. Now, because the integration is Remember, integration is a linear operator, so we can distribute the integral of the terms here. So we can write the integral from minus infinity to infinity of, so we write integral from negative infinity to infinity of x squared f of x dx. The next time we have minus 2 x x bar f of x dx. This is the integral from minus infinity to positive infinity. And the last term we have plus x bar squared. That is the integral from minus infinity to infinity f of x dx. Now notice that the first term here, we just write integral from negative infinity to infinity. We have x squared f of x dx minus 2. 2 is a constant. X bar is also a constant. Then we have the integral from negative infinity to infinity. We have x f of x dx. That's the second term. Because x bar is a constant and 2 is a constant, so we can push them forward. Then the last term, we have x bar is a constant, so we shall write plus x bar squared, the integral from minus infinity to infinity, f of x dx. Notice that here, this integral here will be equals to the mean x bar. This is by definition the mean x bar of the random variable. While this other one here, the integral from minus infinity to positive infinity of f of x dx is equals to 1, because f of x is the probability density function, and this is the integral over the entire region, which represent the total area under the curve. So this is equals to 1, while this quantity here is equals to mean. So in this case, we can note that this is equals to the integral from minus infinity to infinity x squared f of x dx minus 2x bar times x bar, then plus x bar square. So this integral here is equals to x bar, is what we have written as x bar here, and this is equals to 1, so the result just becomes x bar square. And now we can simplify this. We write the integral from minus infinity to positive infinity x squared f of x dx minus 2 x bar squared plus x bar squared, which reduces to the integral from minus infinity to positive infinity f of x dx. There is x squared here minus x bar raised to the power of 2. When we get the difference here, minus 2x bar squared plus x bar squared will give us minus x bar squared. So in this case, this is what we have here. So instead of writing x minus x bar squared times f of x, we can integrate x squared times f of x and then subtract the square of the mean. Now we have an example. A continuous random variable f of x, or rather a continuous random variable x as a probability density function f of x, defined by f of x is equals to kx for x between 1 and 2 and 0 at all other points. The problem is to find the value of k and also to find the probability that the random variable x is less than 1.2. So to find the value of k, first we note that this is a probability density function. F of x is a PDF. So f of x is a PDF, which means that the integral from minus infinity to positive infinity of f of x integrated with respect to x will give us a value of 1. Now, notice that when we are working out this integral, this function is 0 at all points except between 1 and 2. So in this case, the lower limit will reduce to 1, the upper limit to 2, because in all the other region, the function is 0 and the integral of 0 is 0. So what we shall be working out is the integral from 1 to 2 of kx dx, and this must give us a value 1 because it is the total area under the curve. Integration of this will give us a half k x squared from 1 to 2 is equals to 1, and this will be equals to, we can write k over 2, then 2 squared minus 1, which is equals to 1, or even 2 squared is 4, so 4 minus 1 is 3, so we get 3 over 2k is equals to 1, so that k is equals to 2 over 3, so that our PDF f of x, we can write it as 2 over 3x for x between 1 and 2, and the function is 0 at all other points. The function is 0 at all other points. The function is 0 at every other point, but between 1 and 2, the function is given by 2 over 3x. So now, for part B, we want to find the probability that x is less than 1.2. This is given by the area under the curve between negative infinity and 1.2. So we write the integral from negative infinity to 1.2 of f of x dx. Now, when integrating this, we will notice that from our function here, if you start from negative infinity all the way up to 1, the function will be 0. Then between 1 and 1.2, because the function is defined as follows. Between, this is 0. Between 1 and 2, in this interval here, the function f of x is equals to 2 over 3x. At all the other section, f of x is equals to 0, f of x is equals to 0 in any other section except between 1 and 2. So when we start from negative infinity coming this way, the function will be 0 all the way up to 1. And then we want to move now from 1 to some point 1.2. So in this interval between 1 and 1.2, function is 2 over 3x, but it is 0 at all the other section here. So when working out this integral, we need only to consider the section between 1 and 1.2 where the function is non-zero. So we write the probability that x is less than 1.2 will be given by the integral from 1 to 1.2, 2 over 3x. So integrate with respect to x. And this will give us 2 over 3. Then we have x squared over 2 from 1 to 1.2. And this is a half of that x squared 1 to 1.2, which is equals to 1 over 3 into 1.2 squared minus 1 squared. We work out this. You can work out this. This is 1 over 3 into 1.44 minus 1. So we can work out this value. So working out this will give us a value of this is 0.44 divided by 3, which will give us a value of 0.14667. This is the probability that the random variable will assume a value which is less than 1.2. So we have a second example, example 4.1.2. We told that a continuous random variable x has a probability density function f of x, and this one is defined as f of x is equals to k into 3x plus 2 for x between 0 and 4, and then the function is 0 at all other points. So the first thing here is to find the value of k. Then we want to find the mean and the standard deviation of the random variable. So here the function again f of x here is defined as k into 3x plus 2 in the interval between 0 and 4, and then the function is 0 at all other points. So we can write that between 0 and 4, in this interval here, in this interval, the function f of x here is equals to k into 3x plus 2. Any other interval here in this section, f of x is equals to 0. In this section, f of x is equals to 0. It is possible, therefore, to plot this curve or this function f of x, but the plotting may not be necessary here. To find the value of k, we just need to know that the total area under the curve, which is given as the integral from negative infinity to positive infinity of f of x dx, should be equals to 1. The total area under the curve is equals to 1. Now, when working out this integral, this is that we are going to start with some from negative infinity in that side to positive infinity on this side. When we start from negative infinity and move in the positive direction towards 0, all the way to 0, the function will be 0 in all this section. When we start from the negative infinity and move in the positive sense, the function will be 0 in all this section up to 0. So that the integral from negative infinity to 0 will be equals to 0. Then there is the section from 0 to 4. In this section, the function is given by this. Then there is the section from 4 to infinity, where the function is again 0. So the integral will be 0. So the only non-zero section is between 0 and 4. That is the only section where the function is non-zero. So in our integral, this is how we can write our integral. The integral from 0 to 4 of k into 3x plus 2 dx is equals to 1. Then we integrate this. So we write k 3 over 2 x squared plus 2x from 0 to 4 is equals to 1. Then we can substitute x is 4. So this will give us k 3 over 2. Then we have 4 squared plus 2 times 4 is equals to 1. When we work out this, 3 over 2 times 4 squared is 16. 16 times 3 over 2 is 24 plus 8. We get that 2k equals to 1, meaning that k is equals to 1 over 32. That's the value of k. So that our function f of x becomes 1 over 32 into 3x plus 2 in the interval between 0 and 4, and the function is 0 elsewhere. The function is 0 at all other points. The function is 0 at all other points. Now, next we want to find the mean x bar. So we write the mean x bar. So x bar is defined as the integral from negative infinity to positive infinity of x times f of x dx. So we multiply the probability density function with x. So in this case, we get the integral from minus infinity to positive infinity. We have x times 1 over 32 into 3x plus 2 dx. This will give us 1 over 32. 1 over 32 is a constant. Then multiplying 3x by x will give us 3x squared plus 2x dx. And the limits are not from negative infinity to infinity now when we substitute the function, because this between negative infinity to 0, the function is 0. So multiplying x by 0 will still give us 0. So the only section where we have the non-zero value is between 0 and 4. So our limits will be from 0 to 4 and not from negative infinity to infinity. So integral of this will give us 1 over 32. Then we have x cubed plus x squared from 0 to 4. And this will give us 1 over 32. X cubed is 64. X squared is 16. Notice that when x is 0, this will be 0, 0. So that's why we are not including that. If we work out this will be 80 all over 32, which is a value of around 2.5, which is a value of 2.5. This is the mean. X bar is equals to 2.5. This is the mean of the random variable. Now, if we want to find the standard deviation, we denote the standard deviation by sigma. So the standard deviation sigma is the square root of the variance of the distribution. The square root of the variance. So we first find the variance, sigma square, which is defined as the expected value of x minus x bar squared, which we had seen we can write as the integral from negative infinity to positive infinity of x squared f of x dx minus x bar squared. So we had seen that the expression can be reduced to this. So in this case, we write this will be the integral from 0 to 4 x squared times 1 over 32 into 3x plus 2 dx minus 2.5 squared. Notice that here we have replaced the lower limit negative infinity by 0 because the function is non-zero only between 0 and 4. That's why we have the limit 0 to 4, because that's the only section where f of x is non-zero. And in that section, it is given by 1 over 32 into 3x plus 2. Then the mean x bar here is 2.5. We had obtained that from up here. We had obtained the mean as 2.5. So we substitute. So we can now write this is equals to 1 over 32 integral from 0 to 4. So we have 3x times x squared will give us 3x cubed. Then 2x times x squared will give us 2x squared. We integrate this with respect to x and subtract 2.5 squared. So integration now will give us 1 over that 2. The integral of the first term will give us 3 over 4, x raised to power 4. The second term will give us 2 over 3, x raised to the power of 3 from 0 to 4. Then minus 6.25, which is the square of 2.5. So we get 1 over 32, 3 over 4 times 4 raised to power 4 plus 2 over 3 times 4 cubed minus 6.25. So if you work out this, the value is 1.08333. This is the variance of the distribution sigma squared. Now sigma will now be the square root of sigma squared, which is the square root of 1.08333, and this will be approximately 1.0483. This is the standard deviation of the continuous random variable x. This is the standard deviation of the continuous random variable x. So when we want to find the standard deviation, first we find the variance, and then we take the square root. So basically, in this session, we've talked about the random variable, and we have said that there are two types of random variables. There is a discrete random variables, which normally takes the countable values in general, and there is the continuous random variables, which can be taken to be a random variable that assumes measurable values, the values that you obtained by taking measurements, so that it can assume any value in a given interval. Then we have talked about the probability density function of the random variable, and we have said that the probability density function satisfies the condition. If f of x is a probability density function, then it must satisfy the condition that the integral from minus infinity to infinity of f of x dx is equals to 1. That is the total area under the probability density function is equals to 1, because it represents the sum of probabilities in a distribution. We have talked about the probability that the random variable takes some value between x1 and x2, and we have said that this one is given by the integral from x1 to x2 of f of x dx. This is the area under the curve bounded by the ordinates x is equals to x1 and x is equals to x2. This area under the curve represents the probability that the random variable will lie between x is equals to x1 and x is equals to x2. We have also talked about the mean of the random variable, which is also known as the expected value, and is defined as the integral from minus infinity to infinity of x times f of x dx. And we have also talked about the variance, which we normally denote by sigma squared, and it is the expected value of x minus x bar squared, which we can write as the integral from minus infinity to positive infinity of x squared f of x dx minus the square of the mean. So basically, this is what we have talked about in this session. And in the next session, I'll discuss the moment generating function. So bye-bye and have a good time.